All right, in the last few classes, we have studied some general features of the operation of both continuously working and pulsed operations of lasers. We also have studied some experimental schemes of pumping them both optically as well as electrically. Let us now turn our attention to the working of a few specific important kind of lasers. You see, invention of lasers in 1960 has led to an unprecedented proliferation of research activity across the globe aimed at amplifying light in a wide variety of materials. This is because different material would emit light at different wavelengths, of course, coherent light. Let me elaborate you a little. Suppose you have a medium which presents you, which offers you two energy levels between which you can create population inversion. Of course, by taking advantage of some more energy levels, as you already know, and I would not go into detail. Now, suppose these two energy levels are quite far apart, and once you have created population inversion, this, you would of course, when you place it inside the cavity, you would of course be able to manufacture coherent light, but because the energy levels are quite far apart, you will produce coherent light of wavelength which is quite short in say of wavelength lambda. Now you have say another medium which this time offers you two energy levels again between which you can create population inversion, but now they are located rather closely. So in this case, when you create population inversion between them, you will once again be able to obtain coherent light, but in this case, the light will have much longer wavelength because the energy of transition between these two levels is quite small. So wavelength will be large. So lambda 2 may be much larger than lambda 1. So then essentially what then happened? Today there exist countless lasers emitting coherent radiation covering a significant part of the electromagnetic spectrum because different medium can give you coherent light at different wavelengths. So you will be able to obtain light of widely varying wavelengths, frequencies that would span across a wide range of electromagnetic spectrum, providing you coherent light over infrared, visible, ultraviolet, vacuum ultraviolet, and even beyond. There are multiple ways of classifying a specific laser system that can be based on the state of the active medium, wavelength of emission, and methods of pumping. For this course, we adopt the grouping of lasers based on the state of the active medium, that is, whether it is solid, liquid, or gas. And consequently, we will identify the lasers as solid state lasers, liquid lasers, and gaseous lasers. The description of a large variety of lasers can be represented in an orderly and comprehensive manner if we follow this approach. However, there are many important lasers such as semiconductor laser, fiber laser, excimer lasers, chemical lasers, and gas dynamic levels. Of course, there are others, but let us just focus on the 5 or 6 at the moment. The workings of which are distinctly different and do not truly qualify to be grouped with the majority of conventional levels, and they will be addressed, described individually, separately. All right, let us now begin this endeavor with first gas levels. In a gas, you know that the atoms or molecules are not tightly packed, unlike the case of liquid or solid. They are quite widely separated, and that means there are enough empty space between the adjacent gaseous species. A gaseous medium thus presents a condition that is spectroscopically relatively simpler to study. Why so? Because the atoms or molecules forming the gas are quite widely separated. Therefore, the energy levels of an individual atom or molecule is not very greatly impacted by the presence of other species, and more so if the operating pressure is low when the separation is much too big. Extensive data on their energy level therefore existed even prior to 1960, the year the laser was born, because studying them was relatively simple. Spectroscopically studying a gaseous species is relatively simpler. Therefore, lot of effort was concentrated to spectroscopically characterize different gases even prior to 1960, simply because they were rather easy to easy for spectroscopic characterization. And then, as we know, striking an electric discharge is fairly straightforward in a gas. We know it as we have studied the operation of fluorescent source of light in quite detail, because you know, in a fluorescent light, a fluorescent light basically comprises of a discharge tube which contains a noble gas at low pressure, and when you subject it to an electric field by placing 2 electrodes longitudinally at 2 ends of this discharge tube, you can actually create discharge that will comprise of electrons of varying kinetic energy, which actually can transfer its energy through inelastic collision to the gaseous atoms, noble atoms, upon colliding with it. And that way you can actually excite energy states of a gaseous species, and they can be readily populated through inelastic collisions, electrons that is readily present in the discharge. And then in mid-1950s, Nobel laureate Towns, Biswas and Prof also theorized the concept of a cavity in the context of amplifying light. You know that if you have a cavity and a population inverted medium, you can amplify light. You know now very, very well. Therefore, the gaseous medium appeared to be the most attractive active medium to allow amplification of light by stimulated emission of radiation. Just following that approach, because you had a very good spectroscopic knowledge of different gaseous substances, so you can actually choose an appropriate gas. You can create population inversion between those 2 energy levels of your that you thought would be best suited to provide lasing. Then upon creation of population inversion, you can actually place that medium inside a cavity and can actually amplify light. So this approach was followed, and there was a concentrated effort that was directed to operate the very first laser based on a gaseous medium. However, as luck would have it, a flash lamp pumped solid state medium earned the distinction of allowing amplification of light by stimulated emission of radiation for the first time. As you know, it was a ruby rod, that is a solid state medium, when pumped by light emitted by a flash lamp, pulse light of course, showed the very first operation of a laser. So then let us see which one was the very first gas laser. The gaseous medium was not very far away because lot of effort was already concentrated, focused on obtaining lasering emission from gaseous medium. In fact, the very next laser that was operated in 1960 December was indeed a gas laser, namely a helium neon laser. So it was just the first laser operated in May 1960, and within about 6-7 months, lasing was obtained in also in a gas laser that was a helium neon. And once first gas laser operated, thousands of new lasing transitions spanning across wide spectral range have been reported in a wide variety of gases. That is simply because good spectroscopic information was already available for a range of gases. And that's why soon after the operation of the first gas laser, thousands of new lasing transitions spanning across wide spectral range were reported, wide variety. As we move forward in this course, we will know that gas lasers intrinsically offers superior spatial quality as well as spectral quality of the emitted beam. These are some of the important features of the operation of gas lasers. They also provide higher power over some part of the spectrum. It is not that a gas laser can provide high power over across the entire range of electromagnetic spectrum. It is only over some region of the wavelength, perhaps somewhere in infrared and maybe some part of visible. They offer also coherent light of fairly good power. We will know, or you already know, that the gas lasers have some inherent difficulty of producing very high power because the active molecules or atoms density would be small compared to that in solid or liquid, where the active species are much more tightly packed. Helium neon lasers operating in the visible region are indispensable as alignment laser. Even today many other lasers operate, but even today helium neon lasers has been recognized as one of the most important alignment lasers. Still finds lot of application. Then the role of carbon dioxide lasers operating in the infrared. In fact, it operates at a wavelength which is 10.6 micrometer. Compare it with a visible lasers such as helium neon laser, which operates at 632 nanometer. So CO2 laser operating in the infrared have wide-ranging industrial and medical applications. CO2 laser is quite an important and attractive laser. And the multiple applications of another very important gas laser, IGNOU laser, that operates in the ultraviolet and even in deep ultraviolet. There is vacuum ultraviolet, such as the manufacturing of semiconductors, medical applications such as LASIK eye surgery, and various scientific research are also well recognized. The working of these lasers, however, differ from the typical gas lasers. And this will be dealt, of course, in the due course. So what are the different kind of gas lasers? See, you can very well understand that the lasing species in a gas laser can be atoms, molecules, or ions. Therefore, popular gas lasers can be of three different kinds. Atomic gas lasers, where the active species are atoms. Ionic gas lasers, where the light emitting species are actually ions. Ions are basically atoms from which electrons have been stripped off, one or multiple. And molecular gas lasers, where the light emitting species is the molecule. Some of the important lasers representing these three categories are helium neon laser, atomic gas laser, argon ion laser is of course one of important ionic gas lasers, and of course carbon dioxide laser. That is a very, very important molecule. And as you know, in atomic and ionic gas lasers, lasing transitions occur between electronic energy levels, because in an atom, the only energy level that is possible is the electronic energy level. However, when you consider the case of molecule, it is a totally different scenario. The vibrations and rotations of the constituent atoms in a molecule add diversity and richness to the emission from a molecular gas laser. That is because, suppose you consider a molecule like the nitrogen molecule. Here, two nitrogen atoms are actually bonded together. And therefore, in addition to having their electronic energy level, the molecule also will have its electronic energy level. But in addition to that, the two nitrogen atoms can also vibrate about their center of mass. Center of mass doesn't change, but the molecule can vibrate. And while vibrating, the atoms can also oscillate, rotate about their mean position. Therefore, a molecule will also have vibrational energy as well as rotational energy. And just as electronic energy is quantized, so would be the vibrational and rotational energy. This thus adds diversity and richness to the emission from a molecular gas laser. A basic knowledge of molecular spectroscopy is therefore prerequisite to gain an insight into the working of these lasers. And therefore, before carbon dioxide operation of carbon dioxide laser is described, studied, a brief description on molecular spectroscopy will precede that. And this will be taken up in due course. So first then, let us focus on the operation of the atomic gas lasers. There is some very important general feature operation of gas lasers that we must understand. Is an electron, when bound to an atom, can possess only discrete values of energy. Why so? Because you know that an electron, when bound to a nucleus, can rotate only in an orbit into which its de Broglie wavelength fits an integer number of times. That means, suppose if this is the de Broglie wavelength of the electron, it will fit inside this orbit an integer number of times. So that means if lambda is the wavelength of the electron, then lambda into n, which is an integer, would be equal to, if this is Rn, then 2 pi Rn. So electron cannot rotate on any arbitrary orbit. Wherever it rotates, its de Broglie wavelength will have to fit this condition. And in different orbits, that means there are only specific orbits which is possible. And in different orbits, electron will have different energy. And from Bohr's law, you know that the energy of an electron in, say, nth orbit. So this is the first orbit, this is the second orbit, and that way there will be third orbit, and so on. So this, for this n equal to 1, 2, 3, so on. So energy of electron in an orbit, the nth orbit, is inversely proportional to n square. This you know from Bohr's theory of atoms, Bohr's atomic theory. So then, the energy of an electron in an excited state En is inversely proportional to the square of the orbital quantum number, which is n of this state. It is appropriate to examine here the bearing of this inverse square dependence, namely this En proportional to, inversely proportional to n square, on the quantum efficiency of an atomic laser. Let us try to explain this. It's not difficult. Let us try to understand this. So En is proportional to 1 by n square. So for the first orbit, the energy of the electron will be, see, En is inversely proportional to n square. So if we assume that the proportionality constant is A, then we can write En equal to A by n square. So for the first orbit, E1 will be equal to A by 1 square. So it is equal to A. For the second orbit, that is the first excited energy level, this is the ground energy level, will be equal to A squared by 2 square equal to A by 4. For the third orbit, that is the second excited state, it will be A divided by 3 square equal to A by 9. And the fourth orbit, that is the third excited energy level, it will be E by 4 square, it is A by 16. Now, what is the difference self-energy of the subsequent energy level? That means E1 minus E2 equal to A minus A by 4, which is equal to 3A by 4, or 0.75 A. E2 minus E3 is A by 4 minus A by 9 equal to 36 5A. So that is equal to approximately 0.14 A. And what is the next spacing between the next set of energy levels? E3 minus E4 equal to A by 9 minus A by 16 equal to 144. 16A minus 9A equal to 7A. This is approximately equal to 0.05A. So you see the difference of energy between the adjacent energy levels rapidly reduces with increasing excitation, 0.75 to 0.14 to 0.05. So if we actually plot then this energy levels, so this is n equal to the ground state. Next one is N2. So this gap is much more than this gap. And this is again much more than this gap. And the next one will be even closer. And so on. So then what did we examine? We found out that the inverse squared dependence essentially manifests as the electronic energy level getting increasingly closer to each other with increasing excitation. As you increase the excitation, the energy levels come closer and closer. I think you have appreciated this point. So this results in very quantum efficiency of atomic levels. So what we have basically found? We have found that E3 minus E2 is much less than E2 minus E1. Now consider operation of a laser with the third and second excited states respectively as the upper and lower level. We are just, it is just for sake of understanding, we are considering this. That this is anyway our ground level, which contains initially all the species, and let us assume that this is our upper level and this is our lower level. And we are exciting, taking molecule, atom from this level to this level. And for taking a lone molecule from this level to this level, we have to expend this much energy, E3 minus E1. So to create population inversion, atoms from the ground state must be selectively transferred to the upper level. An amount of energy, E3 minus E1, is to be expended to move just a lone atom from the ground to the upper level. Now, a small fraction of this energy, that is E2 minus E1, will be emitted as a laser photon, and rest of the energy, that is this much energy, which is E2 minus E1, stays back into the system and makes no contribution to the laser output. The quantum efficiency of the laser, namely E3 minus E2 divided by E3 minus E1, is intrinsically small, very small. This is because lasing occurs far above the ground state. I think I will stop here today, and next class I will again begin from this point, from here, that why quantum efficiency of atomic gas lasers is so very small.